The next speaker is Eldho Edison from the Laboratory for Multifunctional Materials of the ETH Zurich. The topic of his presentation is enhancing sodium battery performance with freeze-cast NASICON solid electrolytes. The stage is yours. And please turn
Thank
off your
you.
camera when you're sharing.
Yes. Yes. Welcome to my presentation on enhancing the sodium metal battery performance with freeze-cast NASICON solid electrolytes. Today, I'd like to briefly introduce freeze casting process for those who are not familiar with it. It's a fabrication process used widely in the ceramic industry to make porous solid structures with a high degree of open and ordered porosity. So for this fabrication process, we would first make a ceramic suspension, and the figure here shows you a schematic of how the freeze casting process is carried out. And we have a PTFE mold, and this is placed on top of a cold copper finger. So when we pour the ceramic suspension into this mold, due to the directional freezing of the ice crystals in the vertical direction, it would lead to creation of this well-ordered structure. And once we remove the frozen ice through a sublimation process, we can create ordered porous scaffolds. And this short video here, illustrates freeze casting being applied to cellulose nanocrystal form. And we can clearly see how the vertical temperature gradient here. You can see the directional freezing of the gel, which is placed on the mold. And this directional freezing leads to formation of vertical ice crystals. This is a tomography imaging of the CNC form. And when these ice crystals grow in this vertical direction, they push the ceramic particles towards the sides. And once this is removed, we can then therefore generate this porous scaffolds. And so why is freeze casting important for battery field? Because it was recently published that some of the lithium metal battery electrolytes, they have advantages from this low tortuosity porous scaffolds, which enable better ionic transport and provide lower interfacial resistance to the movement of lithium ions. And hence I decided to explore this for the sodium metal battery electrolytes. And when we consider various solid electrolytes for solid state sodium metal batteries, the figure here actually demonstrates the ionic conductivity variation with temperature. And the red circle that you can see here demonstrates the conventional liquid electrolytes. And they have a ionic conductivity of almost 1 millisiemens per centimeter at room temperature, or almost 30 degrees Celsius. And as you can see, the solid electrolytes that are reported in literature that we have available, they are almost several orders of magnitude lower compared to the liquid electrolytes. And the black line that you see here is the ionic conductivity variation for a NASICON solid electrolyte, namely the sodium zirconium silicophosphate dot with lanthanum. And as you can see, at around 60 degrees Celsius, it reaches the required ionic conductivities of a liquid electrolyte. And this is one of the biggest challenges when it comes to solid electrolyte development for both lithium as well as sodium metal batteries. And the advantage of a NASICON structure is that the figure represents a sodium aluminum titanium phosphate. It's the material that I used for this present study. And there are also other NASICON solid electrolytes like sodium zirconium silicophosphate. And all of these materials, they have a three-dimensional framework with a specific arrangement of the metal oxyphosphate tetrahedrons. And the sodium ions will be located at the interstices between these layers. And this framework actually allows the sodium ions to move efficiently throughout the crystal structure with a very less resistance. And this is quite critical when it comes to development of fast charging batteries and so on. And the ceramic powder, I bought it from a commercial source. And after ball milling the powder, it had a size of nearly 200 nanometers. And the X-ray diffraction studies also confirmed good phase purity of the material with the sodium, aluminum, titanium phase, and only minor impurities